session is about two sides of the same coin. One side of the coin has session types, and the other side has game semantics. This will be given by Simon Castellan from Imperial College.
So I'm going to present quickly the two sides of the coin. So first, on one side, we have session types, where you have types, which specify formally some kind of protocols, and you have processes, which describe implementation of those protocols. And then on the other side, we have game semantics, which deal with two-player games, which are also used to specify, to represent some kind of protocols, and strategies, which are also some kind of implementation of those protocols. And the funny thing is that they are used in completely different settings. So session types are used mainly for specifying the behavior of message passing programs so that your concurrent program is correct by construction. Whereas on the other side, game semantics is more used to give semantics of higher order effectful program and study program equivalence there by translating higher order types to some kind of protocols and then programs to some kind of implementation of those protocols. But yet somehow they are very related, and because they have disjoint uses, it's very fruitful to relate them formally. So I'm going to give you an idea of the correspondence at the type level by describing a simple protocol, which looks very much like a simple version of FTP. So in this protocol, the client can connect to the server and request a file, and then the server can answer either the file is not there, or it can answer the file is there, and then give another channel on which the client can download the file. So, for instance, a port where the client can connect and download the file. And that from this point on, the client can close the control channel. So in session types, you would describe the protocol like this by first choosing the point of view of one participant, let's say the client, and then you would have the following type. The type starts by sending a message labeled request. So that's the bang. And then it can receive a message from the server, and there are two possibilities. Either it's absent, and then the file is not there, and then the protocol stops, nothing can go on, or the file is there, and then the client receives a channel on which it can receive the content, and from that point on the main channel, the client can also send a done message. And the same protocol would be described in game semantics based on event structure as follows. Well, now the moves of the games represent messages. So we have rec, absent, found, done, and contents. And now we have extra structure on top of those moves, which represent the rules of the game. So for instance, here rec is the first move that can be played. So we have some kind of causality, which represents the sequencing between the actions. And we also have some kind of conflict, which represent the different branches of computation. So for instance, absent and found are in conflict, meaning that the server has to pick one. But for instance, done and contents are neither in conflict nor related by the causal order, so they can occur in any order. And that's up to the implementation to decide what's going to go on. So even though at this level, everything seems to be working very well, there is a deep difference at the implementation level, because the processes that in session types are considered are usually synchronous, and the strategies that are considered in concurrent game semantics are usually asynchronous, and in a very strong sense, much stronger than people in the calculus are used to. So there is some kind of gap here to be filled if we want to relate those two. And that is exactly what we do. So before our work, that's roughly the landscape. So on the left, we have session types and processes, and on the right, we have games and causal asynchronous strategies. And what we start by doing is to relate session types and games, and actually show that session types can be embedded in game and characterize exactly the image of this embedding. So that shows that actually games are a bit more expressive than session types. Then at the implementation level, we don't exactly know what to do because of this mismatch. So what we did is to generalize the causal asynchronous strategies to what we call coincident strategies, which support a form of synchrony. Then we show how to interpret those processes in a fully abstract manner in those new space of strategies. Then we show how to encode these coincident strategies in the usual space of asynchronous strategies by using the standard trick of using acknowledgements to encode synchrony on top of asynchrony. And then we show finally that all of the causal asynchronous strategies can be defined by a subset of the language of processes that we call Courteous processes, by analogy with the game semantics terminology. And so with this diagram, we have two applications of the correspondence already. We can see processes as a syntax for asynchronous strategies, and that can help overcome the abstract nature of strategies. So we can do syntactic reasoning on them. But also we can have a semantic-driven call return translation of process. So we can take a process, go all the way into the diagram and get another process, which can be run in a synchronous or an asynchronous network without any difference. And that turned out to be very hard to define syntactically. And in this talk, I will just focus on the coincidence strategies and how to interpret process in them. Okay. So first, I will briefly recall the session pi calculus that I'm going to consider here. So it's the binary session types. So first, we have the types describing session or protocol. So it can be either end, so the protocol where nothing happens, or it can be an output selection where the process can choose between sending a label among the LI, and then it can also send channels of type SI along this label. And then this channel has to behave, then the process has to behave on the channel as the continuation type TI. And then there's a dual type for input and branching. So usually in session types, the two are distinct. So we have output and selection in two different constructs, but we use a single construct here to be able to have a nicer relationship with the games. And then the process has a standard pi calculus process where we have parallel composition, restriction, output, and input. And the input does a matching on the label received. In the paper, we have more. We have recursive types and non-deterministic choices, but I'm going to focus on that fragment for the talk. Then we have a typing system, which is a usual session type system, which is linear and guarantees the absence of a race between outputs and inputs. So it ensures that the communication is deterministic. And on this language, you have a notion of contextual equivalence, which here we use the barbed congruence, standard one, that we use for the full abstraction result. Okay, so that's more standard. So now I'm going to briefly introduce the game semantics we use, the game semantics on event structures, where both games and strategies become event structures. So a game here is going to be an event structure, so a gadget of this shape here, where every move of the event structure has a polarity describing either a player move, green, or an opponent move, red. And then the event structure bit, so the causal order here, and the conflict relation encode the rules of the game, as I said before. And then the strategies are also event structures of this kind here, so very similar, plus a way to relate the events of this event structure to moves of the game. So we have a map like this. But usually for the diagrams, I will just draw like this because it's enough. So here, for instance, these strategies implement the protocol by, when the file is found, first asking for the contents and then issuing the done message. But that's one particular choice. Another choice is to issue them in parallel, and that's allowed by the protocol. Or another choice is to choose an order non-deterministically. So here there is a conflict between those two events, and then the computation proceeds in two different orders. Okay, so now that we have games and strategy, we can see how to interpret types as games. And it's actually not so difficult because we simply, in a way, map a type to its tree viewed as a game. So the idea that if you have an input, for instance, so you can input one of the label in the LI, receive a list of channels SI, and then continue as TI. Then the initial moves will be the LI, so it will be reception of the move label L1 or reception of the move label L2. And all of those moves are going to be in conflict because the server or the other party has to choose one. And then there are now new channels of communications because there are all of the SI and the TI. And on those channels, communication can occur in any order. So actually, each of the LI will have one child per channel of communication. So the continuation T and all of the SI. And the same for output with a bit of duality here that I'm not going to detail, but for the thing to work smoothly. And then the context, which in session type is just an assignment of channels to session types. It's just going to be interpreted as another game, which is a parallel composition of all of the types. So the parallel composition just puts the event structure the game side by side without any interference, saying that when you have a context, then the type doesn't give you any constraint on how to use the different sessions. You can interleave them as you want. And then we characterize the image of the interpretation. So the games like this, you can see that they are all forests. It's very easy to see on the causal order. And they are recursive. And that's pretty much it. So if you add confusion-free, then you actually characterize the image of the interpretation. And that's a nice thing because most of the games that we use in game semantics are actually of this shape. So we can really see the games that we use in game semantics as some kind of instances of session types. But interestingly, actually, the interpretation is not injective and actually abstracts away from some of the irrelevant syntactic information, irrelevant from the point of view of computation, of observational equivalence. So for instance, the order of parameter and the continuation type doesn't matter. You can permute them and get the same game. And that means that actually the protocol differs syntactically from the session type point of view, but they are really the same, morally. But the main issue, as I said, is how to interpret name passing. And I'm going to briefly touch on that. So how can you interpret the simple process that sends B on A? So first is to look at the game that it has to play on. So here A has type send L with a channel of type S, and B has type S. So the game, following the interpretation of the 2 slides ago, has this shape where you have a copy of S corresponding to B, and a copy of S dualized, so all the moves have exchange polarity that are following the send of L. And so if we take a concrete example, where S is, for instance, receive label X, send label Y, then we have this game here, where you see the 2 copies. So each move of S has 2 copies with different polarities, and the natural interpretation of this process would be this, where we on the X, so the positive occurrence needs to wait for the negative occurrence. And if you think of what this means, it means that actually you're not sending B, you're sending a fresh channel, and then you're putting locally a forwarder between the fresh channel you sent and B. And because of these arrows here, the forwarder is asynchronous because there is a delay, you see, from the reception X and the forwarding onto the channel sent on A. And this delay is observable when you have a synchronous calculus. And that's why it doesn't really work to model synchronous pi calculus using asynchronous game semantics. So the model, you cannot really have a model which is adequate for a strong notion of convergence. So to avoid this delay, we need simultaneity. And for that, we use an old idea by Gika and Mena to use causal loops. And the idea is to say that we want those 2 events to actually be simultaneous, not to have one and then the other. We want them to occur at the same time. And for that, we can represent this as a causal loop by saying that if X has occurred, then this X has to have occurred and vice versa. But how can we formalize this idea? So first, we can use a little simplification of the notation. So we'll just use a line like this. And to formalize this idea, we introduce coincident event structures, which are just event structures where you relax the hypothesis on the partial order to be just the pre-order. And then you have a bit more structure. You have what we call coincidences, which are just the equivalence classes for the equivalence relation generated by the pre-order. And that means that such an equivalence class represents events that have to occur together. And then we can define strategy using them by saying that a strategy on A is just a coincident event structure S that you can map to A, so that the coincidences have actually a very simple shape. It's either a singleton, so it's an event that occurs by itself, or it's a negative move and a positive move, like in the case of the forwarder. And you can organize them in a compact closed category. And the composition is not so trivial because you have to tell apart the deadlocks from the coincidences because they both, when you do the interaction, they both get seen as causal loops. So it's actually a bit tricky. Now we can interpret processes in a straightforward way by using the synchronous forwarder, which is very similar to what Paul-André Méliès talked about earlier in the afternoon. So the idea is that if you have a game A, you can form the game A per parallel A, which has this shape. And then the synchronous forwarder here is going to relate the two occurrences of every move so that they occur at the same time. And then you can use this operation to interpret the difficult cases of the interpretation. So restriction. So in the restriction, you have two occurrences of P, of A in P, which have dual types. And you can trace them out using copycat. So you write it like this. And if you send B on A, you just issue the label L, and then you continue as P, and in parallel, you set up a forwarder between implicitly the fresh channel you've sent on A and the B. And we've shown that the interpretation of processes is fully abstract, so the interpretation preserves and reflects contextual equivalence. Okay, so there's a bit of related work in this domain. So first, there was quite a few models of event structure for the calculus, but those models, they have an explicit representation of names, and that makes the model extremely difficult to deal with scope exclusion, and the model construction is very hard, whereas here we have more structure. So we work a bit harder to have a nice compositional structure, but when we have it, actually, the model is fairly simple to define. There are also other standard models of game semantics using asynchronous strategies, but that can only work for May testing because of the reason I mentioned before. There's also the model by Hirschowitz and collaborators using advanced categorical machinery, which is fully abstract for fair testing, but their model doesn't account for the causal behavior of processes, which we have here as a consequence of the tool we use. And then, as I said, Paul-André presented earlier in the afternoon a categorical account of coincident copycat and strategies, which nicely generalizes the notion that we have. So we have a more abstract presentation of the concrete object I've presented here. So in a way, strategies can be seen as some kind of causal normal forms of processes, whereas processes can be seen as the syntax for strategies. So in the future, I would like to extend this result to a more explicit calculus by maybe getting rid of the linearity constraints, and which is equivalent to step out of the race presetting, so allow multiple output to race to the same input. And that's all I had to say. Thank you.
Excellent. So I'll start with an anonymous question from the Slido. Does this yield a compilation strategy from session types to possibly higher order stateful programs?
That's a very interesting question. So the problem is that it's not exactly that game semantics model which is used for higher order stateful computation, and I think it's the question already would be at the type level how you read a session type as a higher order type. I'm not sure exactly how to do that, so I'm not sure it could be.
Okay. Any questions from the audience?
What does it give if you try to consider a more general notion of session type, like multi-party session types, something like that? Does it induce something on games and strategies?
So we have some work in progress extending this to multi-party session types, and so we just look at local types, and so then you have several local types which describe the side of every actor in the type. On that, we can give an account in terms of a strategy on a particular game. And then actually we can see how to use the asynchronous copycat to induce the usual asynchronous semantics on multi-party session types. So that's the direction we are looking at right now.
Yes, so you have this interpretation of session types into games, and then you can characterize those games that correspond to session types. But what of the other way around? Can you inform the design of new session types from the games?
I've thought about it. So how to build a more general version of binary session types, which characterizes a larger class of games and how to build a typing system for that. So the thing that's missing in session types is some kind of joins, where you have two concurrent events and you say, you have two concurrent messages and you say, okay, look, I want this message to be able to be ready when those two messages have been issued. And this could be useful when you want to say, for instance, that you want to allow some computation to run in parallel, and you want to say, okay, now there is this last message of the computation, and I want this last message of the computation to only be allowed when all of the messages before have been performed. The problem is that how to write for a type system for such a typing discipline is very hard. And I've had a look, and it seems a bit fiddly. So, but it's definitely something I would like to look into more. But it's very hard from a syntactic point of view to characterize typing.
Okay, so another question from Slido. Any clue of how to introduce replication in your framework?
Yes, so I think I have a pretty good idea on how to do, but so in an earlier paper we have some symmetry which can be used to handle replication, and I think we can use this to handle replication in that case. And then we have to move to change slightly the copycat to have something which is called a saturated copycat, which when opponent plays a move, it forwards this move, not exactly this move, but one move or a symmetric move to it. And that can be used to handle races and replication.
Great. Let's thank our speaker again.